Today we will discuss about the gamma and beta function. So we start new topic, gamma and beta function. So first we take the definition of gamma function. We start with the gamma function. Gamma function basically defined for the improper integral. So it is defined for improper integral. Basically, improper integral means whose limits are infinite or function is not continuous. So improper integral and it is denoted as gamma n. So this is the symbol to represent the gamma. So gamma n, we write down the definition of gamma function. So gamma n is equal to integral 0 to infinity e raised to the power minus x, x raised to the power n minus 1 into dx. So this integral is defined only when n greater than 0. So n should be positive. So this is defined only for n greater than 0 only. And this integral is also called Eulerian integral. Eulerian integral. Okay. So this is the basic definition of gamma function. Now, we have another definition, that means second part of this gamma. To prove that gamma n upon a raised to the power n is equal to integral 0 to infinity e raised to the power minus ax, x raised to the power n minus 1 into dx. So this is the second part of this. That means we also say that this is the second definition. So sometimes we use this definition also in various problems. So when we do the proof of this, so we do the proof of this by using the definition. So we remember the definition. This is the definition. So we know that by using the definition of gamma function, so we write the definition of gamma function. Gamma n is equal to integral 0 to infinity e raised to the power minus x into x raised to the power n minus 1 into dx. So this is our equation 1. So we want to prove this proof. So that means we put x is equal to az. We put x equal to az. When we differentiate this, so we write down a into dz. Now we take the limit. So when we talk about limits, so these limits are defined for x. So for a lower limit, we take x equal to 0. So when x is equal to 0, so when we put x equal to 0, so 0 equal to az. So this gives us z equal to 0. So the lower limit remains unchanged. So x equal to 0, that means gives us z equal to 0. For upper limit, when we put x is equal to infinity. So upper limit is given as infinity. So we write down as infinity is equal to az. So this can be written as z is equal to infinity upon a. So when we divide infinity by something number, so gives us the infinity. Okay, so this is equal to infinity. The limits are remains unchanged. So the new limits we write down as the new limits z is equal to 0 to z is equal to infinity. Now we write down the integral gamma n is equal to integral z equal to 0 to z equal to infinity e raised to the power minus x. So x we put as az into z x. So x we put az to the power n minus 1 into dx. So the what is the value of dx? The value of dx is a dz. So we write down the value of dx also. So dx the value is a dz. So we write down the value of this. So this is the a dz. This is a dz. Now when we simplify this, so this can be written as z tends to 0 to infinity e raised to the power minus az and a raised to the power n minus 1 z raised to the power n minus 1 into a dz. A dz. So this can be written as a raised to the power n minus 1 and to a. So this gives us a raised to the power n, or this is the purely constant. So we write outside from the integral. So we write as z equal to 0 to infinity e raised to the power minus az and z raised to the power n minus 1 into dz. So this is the value of gamma n. Now this can be written as gamma n. So upon a raised to the power n. So this a raised to the power n taking into LHS side. So we divide. So this can be written as z equal to 0 to infinity e raised to the power minus az and z raised to the power n minus 1 into dz. Okay, so now we know that the properties of definite integral. So property of a definite integral says that so when we have function fx into dx from limit a to b, so can be written as function a to b ft into dt. So we apply the limit, that means apply this property here. So we write down this as into the form of x. So x equal to 0 to infinity e raised to the power minus ax and x raised to the power n minus 1 into dx. So this is our proof. So we use this definition also. Okay. So now next we have some properties. So we write down the properties of gamma function. Properties of gamma function. So we start the first basic property. That property is that gamma 1 is equal to 1. So we want to prove that gamma 1 is equal to 1. So how to prove this gamma 1 equal to 1? So we shall prove this we shall prove this by using definition. By using definition of gamma function. So we use the definition of gamma function. So that means this definition is written as gamma n is equal to integral 0 to infinity e raised to the power minus x, x raised to the power n minus 1 into dx. So here in this definition, we put n is equal to 1. in above integral. So we see that in LHS, we write down n equal to 1. So gamma 1 is equal to integral 0 to infinity e raised to the power minus x raised to the power 1 minus 1 into dx. So 1 minus 1 into dx means x raised to the power 0. So x raised to the power 0 is 1. So we write down e raised to the power minus x into dx. So when we do the integration of e raised to the power minus x, the integration is minus e raised to the power minus x, and we put the limits 0 to infinity. So now we apply the upper limits. This gives us minus infinity, minus we apply the lower limit. So minus minus plus e raised to the power 0. So that means this gives us e raised to the power minus infinity or plus e raised to the power 0. This gives us 1. So e raised to the power minus infinity is 0 and e raised to the power 0 is 1. So this gives us 1. So the first property we write down as gamma 1 is equal to 1. So gamma 1 is equal to 1. So remember this one. So we use this property frequently in the questions. So gamma 1 is equal to 1. So you remember some points. So that means we have suppose e raised to the power 0. This gives us 1. E raised to the power infinity gives us infinity, or e raised to the power minus infinity gives us 0. Okay. So that same time we can take log. That means log 1 is equal to 0, and log infinity, it gives us infinity, and log 0 is minus infinity. Okay, so remember this table. So this is for first property. Now we move to the second property. So second property of this gamma function. So second property we take as prove that gamma n plus 1 is equal to n gamma n. Where this is very important property. We use in various problems to solve. So here we shall prove this property also. So by proving this property, so we again use the definition of gamma function. Use the definition of gamma function. So the definition of gamma function means gamma n is equal to integral 0 to infinity e raised to the power minus x raised to the power n minus 1 into dx. We see that the LHS part of our property is gamma n plus 1. So here we put n is equal to n plus 1 in above integral. So n equal to n plus 1 in above integral. So we see that gamma n plus 1 is equal to integral 0 to infinity e raised to the power minus x, or x raised to the power n plus 1 minus 1 into dx. So x, that means plus 1 and minus 1. So we see that this gives us x raised to the power n. So we can write down this as this equal to integral 0 to infinity e raised to the power minus x into x raised to the power n into dx. Okay, so now we integrate this. Integrate. So when we integrate this, so that means this x raised to the power n. So we use here islets. So when we use the islet, so first we have algebraic terms, that means x raised to the power n, then the exponential. So this is our second function. So this is our first function. This is our second function. Now, so we write down as a first function, that is x raised to the power n in integration of second. So integration of second, the integral of second function is minus e raised to the power minus x, and apply the limit as 0 to infinity minus sign of integration 0 to infinity, differentiation of first, n x raised to the power n minus 1 into integration of second. So minus e raised to the power minus x into dx. Okay. So when we solve this part, so basically this part when we put n tends to x tends to infinity. So this gives us infinity into e raised to the power minus infinity 0. So infinity into 0 indeterminate form. So indeterminate form. So when we solve this indeterminate form to make this a 0 upon 0. So this is our first part. So now first parts. So before solving this integral, so we solve the first part. So remember, first we solve first part. Now here we can write down this as, suppose that this gives us limit x tends to infinity, x raised to the power n and e raised to the power minus x. Minus sign we can take a common from outside. So this gives us when we put x tends to infinity, infinity raised to the power something gives us infinity into e raised to the power minus infinity is 0. So infinity into 0. So this gives us indeterminate form. So this gives us indeterminate form. Indeterminate form. So when we solve this, so this can be written as limit n x tends to infinity, x raised to the power n upon e raised to the power x. So this infinity into 0 can be converted into the form of infinity upon infinity. So we convert it into the form of infinity upon infinity. Now, when we have a 0 upon 0 or infinity upon infinity, so we apply the L'Hospital rule. So this can be written as a differentiation of numerator n x raised to the power n minus 1 and differentiation of denominator a raised to the power x. Now, again, we do the same thing. So this can be written as, again, this gives us infinity. So that means we again follow the rule. So that means that can be written as x raised to the power n minus 2 upon e raised to the power minus x. So when we differentiate again and again up to n times, so when we differentiate into n times, so the numerator, that may be apply L'Hospital again and again up to n times. So you apply L'Hospital n times, so the numerator will be constant. The numerator will be constant. That means gives us factorial n. So you know that when we have y is equal to x raised to the power n, or when we do the nth derivative, means yn gives us the factorial n. So numerator will be factorial n and denominator is same as e raised to the power ax. So now when we put n tends to x tends to infinity, so this gives a factorial n upon 0 e raised to the power infinity. So factorial n upon infinity. So something upon infinity gives us 0. Okay. So the first part gives us 0. And when we put limit x tends to 0, so this gives us also 0. So first value will be 0. So now written back to the this integral. So the first part, now first part is 0. So 0 minus second part, that means that integral. So we write down as minus n taken common. So minus minus will be plus. So plus n integral 0 to infinity and x raised to the power n minus 1 e raised to the power. So this gives us x raised to the power n minus 1 e raised to the power minus x into dx. Okay. So this can be written as n integral 0 to infinity e raised to the power minus x into x raised to the power n minus 1 into dx. So here we use the definition, using the definition. So when we use the definition, so definition says that This is the value of gamma n. So here we have proved gamma n plus 1 is equal to n gamma n. So remember, so this is our second property. So we have proved gamma n plus 1 is equal to n gamma n. Now,